Oh, it's good to see so many of you here today. Are we ready to get started? Hi. Great. It's great to see so many of you here today on such a blustery and inclement day, uh, and I think we're going to have a great turnout here. I'd also like to welcome all of those participating over the webcast. We have close to 40 participants over the webcast, and the geographic distribution is kind of fascinating. This is a great topic, I suppose, because we not only have folks from here in Georgia, but Washington, D.C., and New York, and Florida, and maybe even as far west as Texas joining. So this is the beauty of a webcast and the power of this particular topic, which is the nexus of water and energy. I'm Ben Hill. I'm with Georgia Tech's Technology Business Center, ATDC, and certainly love to welcome you to today's program. There are a number of folks and firms who make this series possible, and I'd like to recognize them and thank them for their ongoing support of this series, where we started looking at energy demand in the Southeast, and now we're looking at different aspects and attributes of energy supply. I'd like to thank the law firm Sutherland, Asbill, and Brennan. I'd like to thank our South Face Institute, McKinsey and Company, and then a number of groups here at Georgia Tech who make this happen. The Brooke Byers Institute for Sustainable Systems, the Office of Sustainability, and the Strategic Energy Institute. So thank you all very much for your participation and support. I'd like to mention the upcoming programs beginning in February, going through April. We will look at the smart grid and look at the issues of the reality of the smart grid, data and data management, making sense out of the data which is obtained over the smart grid, and then conclude the series with considerations of plug-in hybrids and their impact on the smart grid. So just mark your calendars for the last Wednesday of the month for February, March, and April, and we will engage those topics. We have some stellar speakers participating in those programs. In terms of logistics for today's program, for those of you who are, the format will be after introductions, presentations by our speakers, then a question and answer session. For those of you who are here, we'll pass around microphones. Be sure to speak into those microphones to help with the webcast. And for those of you participating through the webcast, email those questions to me at ben.hill@gatech.edu. It's ben.hill@gatech.edu. So again, it's good to see so many of you here. I'd like to introduce Dorothy Franzoni with Sutherland, who has a few comments about Sutherland's sponsorship, and she'll begin introduction of the speakers. Thanks.
Good afternoon. I'm Dorothy Franzoni, a partner at Sutherland, Asbill, and Brennan here in Atlanta, and I am chair of Sutherland's Renewable Energy Practice Group. And Sutherland is very proud to be a sponsor of this series that started over a year ago. We have a very broad energy practice with over 50 attorneys in offices in New York, Washington, Atlanta, and Houston, covering virtually all aspects of the energy business, from oil, natural gas, electricity, renewables. And so we have a pretty broad regulatory and transactional and litigation practice in all those areas. And renewable energy, and especially the opportunities for renewable energy in the Southeast, is of particular interest to our firm and to our firm's clients. So I'm very proud that we can sponsor this event, and I'm glad to be here today with you. My job today is to introduce to you the moderator for our panel. We are lucky to have with us today Judy Adler, who is a senior program officer at the Turner Foundation, where she manages the strategic direction of water, energy, and air programs for the Turner Foundation. Her background is in environmental engineering, and she formerly worked for the State of Georgia Sustainability Division, managing a team of engineers that help businesses and institutions across the state reduce their environmental footprint. She has also worked as a consultant with Metcalf and Eddy, where she provided environmental services for industrial, municipal, and federal clients. Judy received her Bachelor of Engineering from my alma mater, Vanderbilt University, and a Master of Science in Environmental Engineering from the University of North Carolina at Chapel Hill. Judy, welcome. Thank you for moderating our panel, and I'll turn it over to you to introduce the panelists.
Thank you so much, Dorothy, and thank you, Ben, for inviting me to moderate this session, one of my favorite topics, as many friends in the audience know. Ben asked me to frame the issues a little bit before handing it off to the speakers. So I thought I'd just talk a little bit about my perspective on water and energy issues. I think Dorothy mentioned that I wear the water and the energy hat at the Turner Foundation. So in a way, I'm at the nexus of water and energy. And as she mentioned, I work for the Turner Foundation, and I have the distinct pleasure of helping Ted Turner and his family with their very modest goal for the foundation to save the planet. So a challenging task that we have. My goal is to help sustainably manage our energy and water resources, primarily focused in the United States. But it's interesting because in my water and my energy hat, I very much work with very different communities, with different NGOs for the most part that work on those issues, with different government institutions that work on those issues, and with different funders that work on those issues. And we're just beginning to try to figure out how to break down those silos across the board. And we haven't figured it out yet, so we would love to get your ideas on how we can do that at the foundation. I do have to admit that we're a bit schizophrenic when it comes to our water and our energy priorities at the foundation. Climate change solutions obviously is one of the priorities that we have at the Turner Foundation. But let's think about what some of the options are for energy supplies to reduce our carbon intensity. One of those options is nuclear power, but what does that mean for our water footprint? I think many of y'all probably know that that's our most water-intensive electricity supply option. And that doesn't get talked about very much. Plant Vogtle that's being proposed here in Georgia on the Savannah River. Ronnie just approved these numbers, so I'm pretty sure they're correct. The expansion's expected to withdraw between 50 and 80 million gallons of water per day. Half of that water is going to be evaporated. And that's enough water to supply somewhere between 1.5 and over 2 million people. So that's a pretty big water footprint. A lot of times we hear about clean coal as being an option to reduce our carbon intensity, carbon sequestration, and storage. Well, if we do that, I'm not an expert in this, but the experts have told me that that will make coal on par with nuclear as far as water intensity. So we need to think about those water consequences of our decisions, and really our institutions aren't set up to do that currently. Plug-in hybrids, exciting topic that's going to be talked about right here in a few months. Well, let's think about what the issues are from a water lens. Again, I'm not an expert in these issues, but I've been told that if we do that, that's going to have an impact on our water resources. If you were to look at per mile a plug-in hybrid versus a gasoline-powered vehicle, it will withdraw 10 times as much water per mile compared to a gasoline vehicle. Now that's withdrawal. Consumption, I think, is more around 3 times if you look at the life cycle. So again, do we consider these impacts when we make these energy decisions? Currently, our institutions aren't set up to do so. Natural gas is a big issue, and at the foundation, we're advocating for natural gas to be a bridge fuel until we can get renewables ramped up to a big scale in this country. And natural gas uses a lot less water at the power plant compared to coal and to nuclear power. But I'm sure a lot of y'all have heard what's going on in Pennsylvania and New York City right now as it relates to hydraulic fracturing and the potential impacts on water quality, on groundwater. So again, it's complicated. Wearing my water hat, I think y'all heard that I used to help design wastewater treatment facilities. Well, if we're going to treat our water to a very high quality, what does that mean? It means it's going to be more energy intensive. So we hear a lot about pharmaceuticals these days in water. Well, we have the technology right now to remove all of those pharmaceuticals from our drinking water. But that's going to be very energy intensive if we decide to go down that path. So again, things to think about. It's complicated. It's not an easy subject. We have a lot to learn about the connections, and I know our speakers today are going to help shed light on these issues. Each speaker is going to have about 25 minutes, and I want to make sure there's plenty of time for discussion afterwards. A lot of y'all probably haven't eaten lunch, so we don't want a stomach growling issue here in the audience. So I'm going to do my best to keep us on track. Our first speaker is Dr. John Crittenden. He's the director of the Brooke Byers Institute for Sustainable Systems with Georgia Tech. His research interests involve pollution prevention, energy and water dynamics, physical and chemical treatment processes, heat and mass transfer, and systems modeling. He's a member of the National Academy of Engineering and is a Georgia Research Alliance eminent scholar. He has a PhD in civil and environmental engineering from the University of Michigan. Please help me welcome Dr. Crittenden.
Well, good afternoon. Wow, such a big crowd already. Such a cold day and blustery out there. I'm glad that you all made the effort to come over here and make your lunches a little bit later than usual. What I want to do is talk about a project that we have with the National Science Foundation on sustainable infrastructures for energy and water. I sort of have to apologize from the beginning that I'm not going to give you an answer, but I'm going to sort of frame the problem that we have. Here's our project team. I'm not going to get into details, but you'll notice that we have folks that are involved with water and energy infrastructure, socioeconomic environment, as well as the physical environment. I'll have to use, sorry, a little technical issue here. Okay. So this is the outline of my talk. I thought I'd frame the problem from a big picture before narrowing in on some of the issues that relate to water and energy. The first thing is, what is the gigaton problem? And basically, there was a study that was conducted by the National Center for Atmospheric Research. DOE commissioned them to run their climate model and ask the question, how much would we have to reduce carbon emissions to avoid the most catastrophic problems associated with climate change? And the answer was 70% by 2100, 30% by 2050. What that means in terms of energy reduction is shown on this slide here. Right now we're about 13 or so terawatts. We'd have to reduce this to about 3.2 terawatts of carbon-based energy. And just so we have a good picture of the other side of the coin, it takes energy to create the materials that we use. You can see this here. We've got it broken down to oil and natural gas, and there's a magic gigaton line right there, 1 gigaton. Oil and natural gas is up here, steel, aluminum, copper, zinc, all the way down the chart here in terms of metals that we might use. You may notice that I've also have on here the amount of energy that's required to produce these materials. One of the biggest ones up here is steel. Also over here I've got it broken down in terms of polymers. Maybe the numbers are smaller in terms of the production as well as the energy use, but I've reported them in here as well. For ceramics, taking a little liberty calling concrete a ceramic, but you'll notice that the energy use is quite high for that, as well as glass and bricks and so on. And then fibers and hybrids over here on the right. Maybe wood we could consider renewable, and some of the other materials that we use in our society. This slide here, if we look at material use, we use about 14 gigatons of material, and the problem is only 5% is renewable. In the long term, it's going to all have to be renewable. And so, and I'll call out one more from here. This is the carbon from fossil-based fuel. It's about 8 gigatons. So the gigaton problem really is about reducing the amount of non-renewables for the material use, and we have to reduce the carbon-based energy by 70%. So that's a tall order. And what I mean by a gigaton solution, or we need a gigaton solution for this, is that if we do a problem or solve this problem, let's say we deal with 1 million tons rather than a gigaton, we need many, many solutions in order to have that add up to a gigaton. Okay, so let's talk a little bit about material and energy challenges that we are facing out there. And I sort of broke this down into two important categories, energy and materials, now that I've sort of introduced the concept that materials and their refinement requires energy. The question that we really have to face here in the future, and I don't know the answer to this, when it comes to energy, is it better to develop green energy production systems or implement existing renewable energy systems? There's a saying that they say that fusion has a great future and always will. Maybe. So anyway, just to give you an idea what I mean there. And materials, so the idea is, do we refine existing technologies that use less energy and materials? For example, can we improve concrete, plastic, steel, aluminum, glass production? Or develop new materials and greenfield technologies that use renewable materials? So this is a challenge. I can show you a comparison that may be of interest to you when it comes to energy production for various industrial sectors. As you may know, China is rapidly becoming, or is perhaps, the energy, is the factory of the world. And you can see here the energy intensity in megajoules per dollar in these various sectors. And across the board, you can see that China is definitely using less efficient technologies in terms of energy production, or energy use to create value in these sectors. So this goes towards a question, you know, how far can we go? Can we go even lower in terms of our energy investment to create dollars in these various important sectors? If you take, roughly speaking, it's about twice as much energy needed in many of the Chinese sectors. The only difference here is agriculture are pretty similar. Okay, so let's talk about how we might move forward to produce energy in a more renewable way. I will get to the water energy nexus soon. There was a study that was done and reported in the Scientific American about how we might create 11.5 terawatts of energy using wind, wave, and solar energy. And the numbers are here. 51% by wind. That would require 3.8 million large wind turbines, 0.8% in place. It would require 1.7 billion rooftop PV systems, less than 1% in place. Concentrated solar plants, 89,000. And then there is some hydro here as well. I labeled this as World War III because the authors looked at the industrialization effort that would be required and is equal to World War II. I don't see the political will at this point for us to engage in such an effort, but it's certainly an interesting idea. And I call it World War III because, unlike World War II, when it comes to climate change, we are all going to be winners or we're all going to be losers. So I got this slide from Paul Denham looking at the renewable energy resources that are out there. You can see wind, concentrated solar plants, and photovoltaics and their adoption across the U.S. So there is quite a bit of opportunity out there. And then in terms of theoretical potential, we can easily obtain the energy that's required. One of the main points that Paul makes is that in order to do this, we need to solve the storage problem. and that is an important issue, as well as the distribution. And I guess later in our seminar series here, we'll hear about the smart grid as it relates to that. And here in Georgia, meeting all of Georgia's demand using PV technologies require about somewhere between 110 and 240 square meters per person. And if we want to contrast that to what's available, the rooftop is about 65 golf courses, urban areas. There's certainly plenty of area around that we might be able to harvest this. But again, the issue will be storage. The biomass part would be interesting because it would require about 50% of the state area for that purpose. So now in terms of another renewable resource that I don't think has been fully exploited is hydropower. We have about 82,000 dams in the United States. Only about 3% of those are being tapped in terms of their energy production. And here in the south, this shows you some of the potential for low power hydro as well as small hydro plants. And then here in Georgia, you can see the potential is quite large. It's on the order of about 4 gigawatts, which is nothing to sneeze at. Three Gorges Dam is about 8 gigawatts. So if you think about Three Gorges Dam as a great opportunity for energy production. Here we're talking about half of that by just dealing with some of the smaller waterways that we already have dams on. So, okay, now I'm going to get to the energy-water nexus. I'm talking about the urban systems. When we think about urban system, in this group we've been talking about water energy nexus, but I'd like to expand that to water energy transportation, socioeconomic nexus. All of those things together are what cause the demands for water energy that we currently experience. So the key thing here is really the land use and intensity type, because this determines how much water and wastewater we have to deal with. It determines the stormwater aspect. So land use is a very important piece of this. We need energy to produce water. We need energy actually for transportation, and also we need, as we pointed out earlier, water to create those transportation fuels. And I have a slide or two on that in a moment. I think there's a tremendous opportunity moving forward as we redesign our urban systems to use less energy and water. And this little graphic here shows that maybe in the next 30 years we're going to invest $41 trillion in this new infrastructure. And the way we've designed this infrastructure in the past is that, I'm from the transportation department, I optimize that. I'm from the water department, I optimize that. I'm in energy production and distribution, I optimize that. But there's synergies between these. And so the idea is that if you look at all of them and their interactions, one could design your urban system to use less resources. And that's really what our project is all about. You can go to our website and get more information in terms of the progress we're making moving forward. One of the concepts, just to illustrate this, is a concept I call infrastructure ecology. We've heard about industrial ecology before, but the same thing applies to infrastructure, is that there's interactions that can occur that reduce the amount of materials and energy that might be required. And the one that we can think of as combined heat and power, suppose we had distributed power generation throughout the urban system, and then we could recover the heat from that and use that for heating the buildings and hot water, or perhaps even air conditioning. You can see what kind of efficiencies you might be able to achieve. For example, if we have a large centralized energy production, electrical energy production facility, for every 100 units of energy we put in, at the plug there, we only get about 29% of that, versus if you had the ability to capture that waste heat and use it, you might be able to get as much as 85% of the energy, 35% of the electrical energy, and then some useful heat here, about 50% of that. So the idea of combining systems and looking at how these systems work together, again, this starts with urban planning, and from there, looking at more compact housing developments is an important part of this. So I'll skip that one. So now I'll start talking a little bit more about some of the numbers for energy for water production in the U.S. Across the U.S., only about 4% of the energy is of the U.S. consumption for energy is for water and wastewater, the water and wastewater sector. In California, the number is considerably higher because they're taking water from Northern California down to the desert, known as Los Angeles, and also water from the Colorado River to the city of Los Angeles as well. But some of the numbers you can see here, depending for water treatment, depending on what it is, surface, ground, brackish groundwater, or desal, you can see the kilowatt hours per gallon that's required. So often surface waters are preferred. Groundwaters, we sometimes have to remove metals and other things. And then for wastewater treatment, depending on the technology you have, you can see the variety of energy that might be required in kilowatt hours per gallon. Okay, so the other way around, water for energy. The numbers that we've already heard today were talked about here in terms of nuclear compared to coal. This is gallons of water per kilowatt hour produced. Perhaps you may not realize that hydro actually uses a lot of water too, because you have this big impoundment, and water we have evaporation. Obviously, this depends on the temperature and the other conditions, but this is sort of a U.S. Average number. So that ranks at the top, with nuclear number 2, oil, and then PV and wind do use water because you need water to produce some of the materials that are invested in the PV and wind power devices. Okay, this is something you may not have thought about, and that is water for transportation. Again, there's a connection between urban planning, the transportation networks, and the water demand that would be required as a result of that. So this shows a number of different fuels here, and it shows the low and high end of water in terms of gallons per kilowatt hour. And you can see that one of the highest ones would be corn ethanol, cellulosic ethanol, and others, depending on algae and so on. And then it also talks about some of the important issues that are involved, whether you irrigate it or you don't irrigate it. That obviously makes a huge difference in terms of how much water is required. But over here on the right, you can see what we're really interested in, and that's gallons of water consumed per vehicle mile traveled over here. And so the solid part is actual embodied in the vehicle, and then the gray area is embodied in the fuel, and the drivetrain and the method that you make the car move along depends on the fuel that you use. And so you can see there's a little variation in terms of the amount that's embodied into the vehicle itself, but you can also see there's a tremendous difference in terms of the use phase as well, depending on what we're looking at. So, for example, there may be some surprises here. Switchgrass with irrigation looks like the highest, and unleaded gasoline looks pretty good. I think we already heard that earlier today. Well, our project really involves looking at both Phoenix and Atlanta, and it's an interesting contrast because we have different physical landscape, temperature, etc. And some of the numbers are pretty interesting. The indoor water use in Atlanta is higher than Phoenix. Outdoor, you would expect to be much higher. It's an arid area, and people still like to have green lawns and green landscape. The residential energy production, kilowatt hours per person per day, is pretty comparable, I guess. For fuel, a little bit more here in Atlanta. Maybe we're spread out and driving a little more, trying to get around. In terms of water consumption for electrical energy production, gallons per kilowatt hour, it's a little bit more in Arizona as compared to Georgia. In terms of water consumption for water supply and wastewater, you can see the numbers are dramatically greater. You have to take water from Lake Havasu over to Phoenix in the Colorado River. So the number is quite a bit higher than it is here in Atlanta. And in the case of wastewater, the numbers are much higher than in Atlanta. So it's an interesting case in point comparing the two cities. Phoenix is certainly spread out as well. Okay, so one of the things that we're working on is trying to simulate how land use would change and what the policy drivers might be for that. And here you see some of the attributes that we've mapped out. We actually have information on 1.3 million parcels in the city. And using a land use model, we can run models like this to compare business as usual business as usual scenario versus compact growth scenario. And obviously this will have an impact on water and energy use, as well as, you know, for transportation, et cetera, et cetera. I wish I could show you what the result is, taking this one step further and saying, well, all right, the energy use for this one is less or different than the energy use it is for this one. But our hypothesis will be distributed, decentralized water and energy production might have an advantage in terms of resiliency and efficiency. Let me just skip over that. Well, there's this concept called low impact development. We're really getting close to running out of time here, but there's a variety of technologies that we could look at that would reduce the amount of water that we use. Certainly green landscaping. In Metro Atlanta, one of the problems we have is stormwater. And it's been estimated that if we increase the tree cover from 29% to 40%, we might actually reduce the storm runoff by 20%. One thing I didn't mention in this compact living area, if you have compact living, so people occupy one building, you're going to have more green space. You can use that green space for what's known as blue belts. The blue belt is where you're trying to control the stormwater and perhaps reuse that for purposes of fire, or even using it for landscaping, that kind of thing, water for landscaping and the like. So another one that would fit under here is rainwater harvesting. And then under water reclamation or wastewater reclamation, it turns out when you look at it, you would actually use less energy. Rather than having a centralized plant, well, our whole city has been built on the Romanesque idea of large pipe thinking. And that's served us well. Basically, you scrape off the ecology, put your buildings in there, hardscape, and that creates a stormwater problem that you have to deal with. So there's some issues there. Now, instead, if you have, and then you have a central plant to collect that water, et cetera, and you have a central plant that would treat the surface supply water that would then, in turn, be used for drinking water. So that served us well. But now if we could do this differently, where maybe we could have decentralized distributed plants, less run times, and we don't have to build such big pipes, there might be some advantages. So that's a concept. Anyway, looking down a list here, one way to do that is, of course, at the point of use, you reclaim that water and use it again for something else. Energy and nutrient recovery, that's very important. We already know that we can recover some of the anaerobic digestion gas from the energy material there's organic matter in the wastewater, and that organic matter could be used for energy production. That's certainly important. And I also might mention that another idea might be urine separation. A lot of the phosphorus and ammonia are there, and we make ammonia. You know, it takes 55 megajoules per kilogram of ammonia. So now if we could recover it and reuse it, that might have some advantages. And also there's an issue about phosphorus. We don't have an unlimited supply, depending on whether or not we think that Morocco will really be a good source of phosphorus. We might have 200 to 300 years of phosphorus left. So at some point, sending phosphorus in a dilute concentration in the ocean might not be the best idea. We also have efficient small fixtures and the water sense products and so on. All right, other opportunities. Okay, energy for transportation, the story here in Atlanta. We are going to also do the water for this as well, but here this shows the megajoules per person kilometer for the various strategies: gasoline, diesel, compressed natural gas, E85, various kinds of hybrid vehicles. So this is the energy production. And then over here, this is the CO2 output per person. This is grams per person kilometer. It seems that I've lost the most important one. This is MARTA over here. That's the worst. And the reason that MARTA is not so good is that the ridership is low. And also, a lot of the electric vehicles don't look as good as just a standard conventional gasoline vehicle because the poor performance of the power plants here, the existing plants, emits about 0.9 kilograms of CO2 per kilowatt hour. Okay, just in time. A few concluding remarks. Well, not all news is bad. There's this genuine progress indicator that Marilyn, I see Marilyn's here, that Marilyn Brown was working on. And you can see that in general, we see an improvement depending on whether you're in the urban core, suburban ring, or the fringe. They're all trending upward. And in case you don't really know what the genuine progress indicator is, I just want to say that it's a measure of 4 dimensions of sustainability, including economic, social, environment, and resources. So I guess you can study that graph and learn a little bit more after you go maybe Google the genuine progress indicator if you don't know what that is. Well, my last concluding remark is this. We really need to recreate the atmosphere that's the place we live, that uses resources that nature provides and generates waste that nature can no longer, that will not overwhelm natural cycles. And I can cite two where we're failing miserably. When it comes to CO2, we're emitting more CO2 in the atmosphere than nature can pull out, so we're failing miserably there. And when we talk about using renewable materials, we know that we're failing there. Only 5% of the 14 gigatons of material that we use in the world economy is renewable. I should also say, when I mentioned that gigaton problem, is that gigaton problem exists for the golden billion, us. And if we really want to think from an egalitarian point of view, where everyone has equal opportunity, by 2050 there's going to be 9 billion of us. And so we better multiply that by 9. So anyway, this will require us to examine the interactions between natural and engineered and social systems. So thank you for your attention.
Thank you so much, Dr. Crittenden. I just love that presentation, and I'd love to steal some of your slides and invite you to speak to other audiences. Really enlightening. It's now a pleasure to introduce Dr. Brennan Smith. He's program manager with the Wind and Water Power Technologies at Oak Ridge National Laboratory. Dr. Smith's work focuses on energy, water, and environmental optimization and hydropower thermal systems. Specific interests include the energy-water interdependencies in regulated water basins, water use optimization for integrated river systems, and the effect of hydropower on water availability and riverine ecosystems. He has his PhD in Civil and Environmental Engineering from the University of Iowa. Please help me welcome Dr. Smith.
Well, thank you. It's a pleasure to be here. Thanks to the folks at Georgia Tech and the sponsors, Ben, for having me here. You're going to get a little different perspective from me. What my intro didn't say was I spent several years with the Tennessee Valley Authority, helping to manage the river system and the energy system, the generation system there, right at the nexus of those two systems. So a lot of what you're going to hear from me comes out of that experience, as well as the last 5 years of Oak Ridge National Laboratory. So I'm going to talk about the energy-water nexus at regional scales. By regional scales, I mean of the southeast and at the scale of river basins. I'll jump right into that. I'm going to talk about the basin scale and regional energy and water systems and how they interact. And at that scale, what is the nexus of the energy-water nexus that we're talking about? I'll give you a specific example of the Cumberland River in Tennessee. Then I'll talk a little bit about how we have to think about and manage the variability and timescales in energy-water systems. And then finally, I'll look at how we have to think about treating non-energy objectives as we deal with energy and water systems and the problems that they bring, not necessarily problems, but the solutions that we have to think about developing in both the energy and water domains. So just a little bit of background and a primer. I apologize if some of this is old hat for some of you all, but When we think about water resource systems, we're talking about inherent uncertainty there in what the inputs of those systems are going to be. We're also talking quite a bit about conflicting priorities. That shouldn't be a surprise to anyone. And those priorities are conflicting at several scales, the metro, the local, and even the basin and national scale. We have multiple demands on the river systems, flood damage reduction. My friends at the Corps of Engineers have taught me not to say flood control because we don't control floods, we just reduce them. Water supply, you've already heard quite a bit about, and I won't spend much time at all talking about how we manage water supply, just that it is a demand. We have to make provisions for the ecology, and we have to manage how we provide for those things. We have to allow for commercial navigation. Certainly in many river systems in the country, we have to provide for that. And that is also a way that we transport things like fuel, whether it be liquid fuel or coal for power generation. Recreation and aesthetics come up oftentimes as we license and do assessments of energy, and then we have to deal with energy supply. Some of the complexities there. Uncertainty, of course, reigns in those systems. There are many, many stakeholders who have diverse priorities. This perhaps is not always thought about, but those priorities are context-driven, and so they shift. When we look on the left side here at these different uses and priorities, when you're in a wet period, obviously flood damage takes priority. But when you get into a drought period, some of these priorities flip, and we begin to worry more intensely about things like water supply and getting people to have things to drink before, and did we do that before we get them energy? These are the questions we have to answer, and depending upon the context we're in, both in terms of development and technology, these priorities can change. And then we have lots, and when we talk about energy systems and water systems, how they interact with the ecology, we have many data science and technology gaps between the decision variables and the outcomes. Decision variables are things like, at the long term, whether to build or not a project, whether it's justified or feasible. At the shorter time scales, we're talking about when we release water and where we release water from, and what elevations we hold in reservoirs and streams. So just real quick, very basic slide on hydrologic future reference. Here's the Atlantic region here, and then we have the Tennessee region right above that, and we'll speak about those two things. Just to give you a sense and remind everyone about the hydrologic structure that we deal with in the U.S. So, electric power systems, the other side of the energy-water nexus, characterized by evolving complexities and emergent complexities. That is to say, we've been going for many years with baseload energy and hydro supplying our needs. As we add things like wind that have variability, solar that has variability, both spatial and temporal variability, we begin to get different types of behaviors depending upon the demand and the supply and the resource for those different generation sources. And so there are many, many behaviors that we're only now beginning to understand, both in terms of joint variability. How does it blow? Does the wind blow when the sun shines? Does the wind blow at night? And how are those correlated with water flow, for example? So we have to understand those emergent behaviors of the generation sources, and that's a source of complexity. So we have multiple asset types. I've listed the traditional nuclear, coal, gas, and hydro here. Typically you have base load plus flexible hydro. Now we have a second tier of wind, solar, hydro, could also include marine energy, and geothermal. We also, at Oak Ridge, have a lot of folks that are looking at demand response. We tend to treat that as an asset sometimes because it helps us balance things in the power system. And then energy storage was mentioned before. And here we've got both pumped hydro as the current only the utility scale storage medium, and then we have things like flywheels and batteries for shorter term distributed energy storage. We have a capacity limited transmission system, not so much an issue for us in the southeast, but very much an issue for folks in the west. And then we have multiple constraints and costs in the power system. Of course, always supply equals demand instantaneously, but we have reliability standards that are in flux. We have security goals that we're trying to achieve by changing our fuel mix. We have fuel supply issues, whether it's how do we deliver coal, how do we deliver uranium for nuclear power production, and where does that come from? We certainly have emissions goals that have been alluded to before. on reducing our carbon intensity of the generation sector. We have changing environmental impacts. We're beginning to understand those, things like in-stream flows. And then we have issues, certainly with initial costs and project financing in the electric sector. Not only with things like nuclear plants and how do we finance those, how do we get those built, given that all of the indicators are there that we need to build them, how do we get them financed? When we think about big hydro projects and big pump storage projects, we also encounter that issue of capital costs. And how do we get these projects financed? The complexities there, we have multiple evolving markets for energy and services. That is for both selling energy in terms of megawatt hours and selling services like capacity services and reserve and regulation services. And I'll show you a couple of slides in a moment on those. We have both mature generation technologies here. We have evolving or emerging systems. Wind is getting deployed or built out, if you will, as is solar. We have newer technologies that are yet to get over the commercialization hump and are coming into play, but they all have different cost trajectories. For example, in the nuclear sector, as we think about nuclear water intensity and moving from wet cooling to dry cooling, we see a cost increase in terms of nuclear O&M costs and nuclear capital costs. Whereas when we look at some of the newer technologies of wind and solar with continued investment in R&D, we see a declining cost trajectory of getting that price down in terms of cents per kilowatt hour. And then finally, we have tremendous uncertainty in national, regional, and state energy policy. Where are we on a federal RPS, for example? Where are we on state RPSs? In the Southeast, we're not that far with state RPSs. Renewable portfolio standards is what I'm saying there. And then in terms of complexity in the power system, we truly do have a system of systems when we think about the individual unit, power plant, power system levels. So in the power system, we have the physical transmission grid here. You see we're very lucky in the East that we have a fairly well-developed physical grid system. So when we want to place generation, it's not quite as constrained in terms of where we can place that as compared to, say, siting wind resources here in the Midwest. So that's something we're fairly rich in terms. And we have here the reliability and control network of the power system, where you see the control centers. So this is where we make sure that we balance load and demand at all times. And this has an impact a lot of times on the institutional barriers to things like sharing reserves, sharing capacity across these balancing authorities so that we can integrate variable renewables. And then finally, we have certainly evolving electric power markets. We in the Southeast are still in the midst of our vertically integrated utilities, TVA, Southern Company, Duke, and others. But we have emerging power markets, the PJM, the Northeast markets, the Midwest, ISO, California, where not only do we have energy markets for megawatt hour blocks, but we have markets for reserves, we have markets for regulation, and other services. Those markets drive the developer behavior for the generation mix of renewable technologies. They affect how much does it cost to bring in wind energy, how much does it cost to bring in solar energy. They affect the revenue streams that affect the financing that get those projects built. So, water for energy linkages, a few things that I'll talk about. In nuclear, of course, we have cooling water requirements. You saw a lot of detailed numbers before on those per megawatt hour and per megawatt. We have waste assimilation, even at nuclear plants. For coal-fired generation, we have cooling water. We have ash handling and waste assimilation. We also have emission control systems on coal. At the extreme, of course, there's carbon capture and storage and the water intensity of that. But we also have things like scrubbers. And an anecdotal story, every day when I go to work at Oak Ridge National Laboratory, I drive by Bull Run Steam Plant, which is about a 965 megawatt steam plant that TVA runs, coal-fired steam plant. They recently, it's a once-through cooling plant, so it had very low consumptive use, lots of once-through use. They now have a scrubber to control their emissions. And now every day, 24 hours a day, there's a huge plume of water coming out of the top of the emissions control equipment as they scrub that, and that water goes up. So they've gone By reducing their air emissions, now they've increased their water usage. So we have to be mindful of that. And to my knowledge, that is not an area of water use intensity that's received a lot of attention yet. There are people looking at it, but on a regional and national basis, that's an issue that needs some more research. Of course, if we do combined cycle, we have to cool that, so there's cooling water demands there. Hydropower, very mature technology in some senses. In others, there's some new technologies in small hydro that can come online. But there's a real uncertainty at this point on water and storage and the availability of flexible hydropower, storage hydropower. Most of the new development that occurs, particularly at non-powered dams, will be at run-of-river plants where we don't have any ability to store water. And it is a storage aspect of hydro that is so valuable. And when you look across the country, and even in the southeast, as plants are relicensed, non-federal plants are relicensed, they typically lose flexibility. They lose capacity factor. And so we don't get as much energy or flexibility for a robust power system as the policies and the constraints that govern hydropower operations are put into place. Of course, there's bioenergy. You heard a little bit about crop irrigation. We have to think about that, the water demand for the refining process. If we use that in the steam cycle to power that, then we have to look at cooling water there as well. I put a brief picture up here to show the hierarchy that has to be in place typically in a hydro and a power system where individual units have to be dispatched at the proper efficiency to make the best use of the fuel, whether it's water or coal or nuclear. Then we have to select across units and select the right units, the right unit commitment and mix of units to get the most efficiency at a given power plant. First, then we have to select how we move water through the system in hydro plants. But in the southeast, we also have to think about, and I'll show slides later, about how we move water past thermoelectric plants for cooling water demand. It's a big issue. Certainly in the Tennessee and Cumberland rivers, I suspect it's an issue that can be improved in other river basins as well. And then as we have an evolving mix of renewables, we have to think about how the influx of renewables, the penetration of renewables, whether it's wind, whether it's solar, or other variable renewables, will change the way we dispatch and commit thermoelectric units and hydro units. And so that'll change the efficiency of the entire system. And so those are issues that are being studied within DOE programs, the wind program, the water program at the Department of Energy, and the solar program as well. This slide comes to us courtesy from TVA in 2010 from their financial reporting, where they did some analysis looking at the different utilities across the southeast. And what we're showing here is the percent of those utilities' fleet or capacity that's going to be retired on this side and the new generation that's planned in the 2010 to 2016 timeframe. And so this is important to know or to think about because we have renewables here in green, we have gas here in the yellow, nuclear in the blue, and then coal in the purple. And so you can see a mix of water demand here in the near term for generation build-out. And so you're going to see, as if we, for example, replace coal with gas, we may see a water reduction there, for example. Certainly, if we see a growth in coal, you're going to see more water use there. And so there's quite a bit of near-term shift in water usage that's going to occur in the generation sector across the southeast. So let's get specific. What are we talking about with thermoelectric cooling water? Well, here we've got a once-through plant, very large power canal that pulls water into the plant and then discharges that water once through. There are temperature and environmental constraints on that water that have to be managed from day to day and even hour to hour in some cases. And as we learned in the most recent drought in the southeast, that doesn't always work so well. And that sometimes these plants can literally be shut down when the water is unavailable, or when the assimilative temperature capacity of the water is unavailable. When the water is hot, there's not enough flow in the river to assimilate the heat coming out. And so we have constraints on generation. We also reduce the efficiency of generation when that happens. This is a generic plot, but it's typical of a steam cycle power plant where the percent of full load, we start out here at 100% when everything's nice and cool in the river and we're pulling water in. And then as you get higher and higher temperatures, you begin to degrade efficiency. You reach a break point in terms of the mechanical operation of the equipment inside. The steam condenser actually have to start scaling back your heat input. You drop further. And then if you're a nuclear plant, you reach a safety limit in the river where you literally have to shut down to ensure at all times you can safely shut down reactors. And so these are real constraints. They're affecting current plants. They're affecting proposed plants that are going in. Here we have cooling towers with consumptive use. That can become critical, particularly during low flow periods. And also when we go to cooling towers, we trade, this is an important point, we trade water temperature dependency for air temperature dependency. And if we're looking ahead toward increased variability, we have to be worried about air temperature variability as well. And the ability to forecast the performance of either the once-through system or the closed cycle cooling tower system is critical from hour to hour and day to day to manage ourselves through low flow drought periods. We've seen that over and over again in the Tennessee River system, in the Cumberland system, that we get into these low flow periods, and the alternative is to overbuild on cooling towers. And that increases of course, our capital cost and the cost of energy or electricity for thermoelectric. So additional details. Here's an interesting plot that I put together. This is the Tennessee River at Chattanooga. And so you have two nuclear plants sitting upstream of this location. You have one major nuclear plant in the TVA system sitting downstream of this system. This aqua hump you see here is the historical history of water temperature at this location with the minimum and maximum plotted. These lines running through are particular single-year trajectories through that system. So you see quite a span of temperature variation from the min to the max history. The blue plot is water flow, river flow here. And so you see the challenge that we have in the southeast with thermoelectric and water availability and temperature availability. We have high temperatures, we have low water flow. And so we get the loss of an ability to assimilate that heat. And if we get an extreme temperature up here, we get an extreme low water temperature down here, things have to shut down. And this problem is getting more and more complex to manage as we look ahead toward climate variability and increased variability. It's also getting harder to manage as we look at increased constraints on water use in the system. So even without climate variability and changing climate, we have increasing pressure on this kind of system to keep everything running through the low flow periods. These are some typical temperature limits here and other extremes that when we get up above these things, operations have to start changing. And then you can see here's a typical way that a thermoelectric plant or utility would look at these things. We've got water flow and air temperature on two different axes. And so when we have hot, dry conditions, that's when we get into trouble. When we have cool, wet conditions, that's usually not so much of a problem. And of course, when we think in terms of climate variability, we're talking about, does this map start to change over time? And do we see shifts going on? And that's when we begin to start worry and have to start thinking about adaptation of cooling tower designs and things such as that. I'll skip over this, just a real quick slide on water and intensity of water withdrawal. This is based on 2000 data, so it's a little dated at this point. But you can see both in terms of once through and consumptive use, we're fairly intense in the southeast, no surprise there, because of the large number of central thermoelectric stations that we have. Hydropower. What are the issues with hydropower and water energy? We have an aging infrastructure in the southeast. Our Corps of Engineer facilities in the Cumberland and in Georgia and Alabama are getting older. They need investments in the infrastructure to make them reliable. As I mentioned before, we're getting increased water management constraints that limit the flexibility and the value of hydro as a dispatchable asset. However, environmental technologies are emerging. Some new things. I won't go into details on those, but things like oxygenation, aeration of water, re-regulating flows to provide minimum flows automatically. And as you heard before, there are some small hydropower opportunities on non-power dams, on potentially on some greenfield sites. What we're finding, however, as we look toward publishing a new report on small hydro opportunities, is that most of the opportunities are at large main stem navigation dams. You look at the energy available nationwide, 60% of it is at these very large dams. The remaining 40% is what's distributed out at the very small dams. These two plots here are shown. They're just for the Tennessee Basin and the Atlantic and all the Atlantic basins on the seaboard. It just illustrates the point that we've confirmed basically that hydro production over the years tracks closely with runoff. It does not always track with precipitation. So it means that we need to be making sure we're continuing to develop and do a good job of being able to accurately predict runoff. And so if we start to see changes in things that affect runoff at the basin scales, we're going to have issues with hydro production. We need to stay on top of that as an electric utility industry, as consumers, as water managers. A real quick example, since time is short here, but this is the Cumberland Basin here. It discharges into the Ohio. It sits atop the Tennessee River Basin. It has several Corps of Engineer dams that produce hydro that's marketed both to TVA, and some of the hydro goes to utilities across the Atlantic seaboard. There are two large thermoelectric plants on the river that are once through that depend upon water. And we've mapped here, this was a project we did a couple of years ago, mapping the blue water flows through the components of this system and the different uses, and the red being the energy movement through those systems. And one of the key issues being that there are different boundaries for the water system and the energy system. And so while we don't have much interbasin transfer of water going on here, we have quite a bit of transfer of electricity from that water going out of the basin. So when we talk about the energy-water nexus, one of the real challenges is alignment of the boundaries of the energy and water systems. And if we are trying to do balances on energy and balances on water and compare the two, we really get into what are the boundaries for that system. Just a quick slide on different institutional perspectives from that study. You had the Corps of Engineers and the way they managed the system. They also managed it for coal, to move coal through the system. TVA uses that system for some hydro flexibility. This is the Southeastern Power Administration, and they market the power. Here's the Corps of Engineers administrative districts, and then we have 305 and 303 lists of impaired watersheds that impact the things that you can do both with moving water through those systems and things you can do with effluents into those systems from energy production. I'll wrap up with this, or close to wrapping up with this slide. One of the important things about the energy-water nexus is the concept of temporal variability. If you look at I've put together a logarithmic chart here going from fractions of a second all the way out to centuries. And if we look at the physical system here, the geomorphology in the river systems, the water use, the movement of water quantities through that system, they span a certain range of time scales. Then we can lay on top of that the ecology of the system, from individual organisms through populations and their responses. And those range from very fast responding organisms to long-lived species that can respond over a century. Sturgeon being one example of a long-lived fish. And so they evolve and respond over those time scales. Then we get into the anthropogenic systems here with the detailed dynamics of power systems. Then we get into markets, both for energy and water. And we have those short-term dynamic and transient time scales that things can get screwed up on those scales. Then we get into market scales of hourly and blocks of energy. And then we get into planning scales for planning for new generation, planning for new water infrastructure projects. When we look at any particular slice through this at any particular time scale, you're cutting across these basic physical systems, the ecology, and the anthropogenic systems. And if we don't have models that can resolve things at those time scales, then we're going to have issues at overlooking issues and problems. So this implies that we've got quite a tall order to develop interrelated or communicative modeling and forecasting systems that can transmit information across these different systems, so that we take care of the physical system and how we modify it. We take care of the ecology and how we affect that. And and we deliver water and energy to people when and where they need it. This is a slide that shows the complex objectives when we talk about making decisions in energy, water, space. We typically work down here at this low level where we're dealing with water quantities. We're dealing with energy quantities, things that are fairly easy to measure. We typically, however, want to achieve objectives in terms of ecology way up here. We want to make sure we have good ecological communities, healthy and robust reservoirs and river systems. So how do we make decisions? Well, there's an array of built-up model complexity that has to be there to get us from the basic quantities that are moving through the system up to the result of, yes, things are healthy. And so currently, when we look at scheduling operations, when we look at things like environmental assessments, relicensing plants, we're typically looking maybe at this level where we're doing water quality models. What we don't have are ecological models that are well integrated here that can allow us to make good decisions. One example of that that's developed at Oak Ridge, and this is for salmon, but it could also be, there are similar models that could be constructed for the life stages of southeastern fish species, but we can actually model the life stages of salmon, and for different water availability in certain basins, if there's high water, then the optimal shape to optimize populations of salmon is one shape. If we have very low water, it's a different shape. So these models are very complex. There's a lot of science gaps in terms of the response of fish and populations and communities that has to be better understood. And the mathematics here are far different than they are for energy and water systems when we talk about optimizing those. So there's quite a lot of development that can occur to marry these kinds of ecological models to energy and water quantity models. And I'll wrap up. Important takeaways. Energy and water systems are connected across multiple timescales, and they have non-aligned boundaries. We already have examples of electricity flowing across hydrologic boundaries. Energy and water systems would benefit from joint analysis of operational and planning timescales. The water use trade-offs exist both between energy and other competing uses for the water, but those trade-offs also exist between different energy technologies, and which ones do we use. I want to point out that the Southeast is very dependent upon water for baseload generation. That's not going to change in the near term. What are the trade-offs when we look at the main renewable being bioenergy? What are the trade-offs between baseload thermoelectric water usage and bioenergy water usage? And our ability to model the ecological implications of these types of decisions and choices is very limited, and we've got quite a bit of work to do there. And with that, thank you.
Thank you, Dr. Smith. And if both the speakers could join us up front, we're now going to have a Q&A session. Do we have questions from the audience? Come on, don't be shy. You know, if you could come up here, I apologize. We don't have cordless technology here. We do now.
I apologize for my voice. The presentations were interesting. I'm curious about the importance of the Great Lakes in our water, energy, and industrial future, as to their importance and how they're going to come into play in the next 50 years. And is it a good time to start buying real estate in Cleveland and Detroit right now based on their forecasts?
In terms of water for energy, there's quite a few. There's quite a bit of thermoelectric generation on the Great Lakes. There's also, in terms of, and that's probably what I could speak to in terms of energy for water production. I probably would defer to you on that.
Yeah, well, I think interbasin transfers are tough in terms of transferring water, so I think that's probably not there. And I don't know what the total capacity of the Great Lakes is yet that hasn't been utilized by the power industry, but I think the numbers are, I've forgotten the numbers actually. There's already quite a bit of power production on the Great Lakes. And, but I guess, that's still going with the idea of a centralized approach where you'd have a centralized plant. And one of the ideas that I was trying to promote here was decentralized and then have combined heat and power. That might have some advantages. Not to mention the fact that perhaps the grid might be simpler because the distance you go from where you produce, where you use is smaller. Yeah.
Hi, Ken Ostrowski from McKinsey and Company. Thank you both. Outstanding presentations, and I think you really crystallized the complexity and criticality of the water and energy trade-offs. One of the questions I have is, as we think about how we move forward and start to take on some of these issues, the big challenge is we don't have a good unifying market or mechanism to help make these trade-offs. So, we have trade-offs between thermal and evaporative cooling. We have trade-offs between agricultural use of water and power use of water, drinking water. And in some of the other complex issues that we face, like carbon,
Carbon, of course, we've heard a lot about. I don't know what price you have to get it to really start to make people think carefully about the use of carbon-based fuels. But,
I think certainly on the energy side, we see that the markets seem to be doing a fairly good job of solving some pretty tricky problems in variable renewables, where we have those markets for short-term services. They help things clear, and they give people certainty in terms of what the revenue streams are on different energy technologies and energy development projects. In the water domain, pricing, I think, I don't have a solution for you there, but I think pricing comes with some issues that have to be dealt with. How does the ecology buy its water, and what do we do with that piece? Do we mandate in-stream flows, for example, and how do the markets function in low flow periods when that's all there is, and there's none available for purchase, and then there's issues of equality with pricing and affordability. How do we ensure affordability? Which I'm not an economist, so I would defer that to an economist. And in terms of there's an interesting dynamic out west in western states, where, for example, where the Bureau of Reclamation provides very inexpensive water and very inexpensive power, and you see a whole host of different types of behaviors for water use and energy use because of those pricing structures. I'm not sure that's going to bring solutions for us. It might bring some additional places we shouldn't go in terms of structures.
Well, in terms of markets, I think it's very important for us to create a domestic market for renewables, because that's going to drive the price down. There's a cost learning curve. I didn't show it to you, but basically, as you increase the put in place renewables, the price reduction is about 20% for every 100% implementation, something like that. And I guess the question that we all have to ask ourselves is whether or not, we're going to be the leaders in terms of producing the best renewable energy technologies, or is it going to be China or India or some other place? What's really interesting is to take a look at Germany, and the solar irradiance in Germany is considerably less than it is in Georgia, and somehow through the feed-in tariffs, they've created a tremendous market for that. I think 5.5 million people work in Germany in the renewable energy area, and that's more than their car industry, which is number 3 in the world, and that happened in 20 years. So the market has tremendous potential. So I think it's very important for us to create the domestic market, however we do it, so that companies like First Solar, which did move to Germany and became a German company that was originally from Toledo, Ohio, moving to Phoenix and eventually over to Germany, We'd like to keep more of those folks here in the U.S. creating greener, greener technologies for energy production. One thing we got to keep in mind is that the carbon-based energies have a 100-year head start. They have the infrastructure. So it's going to take an awful lot to build the same amount of infrastructure for renewables. I always get a chuckle when I fly into Reagan Airport and there's a plaque on the wall that says 9.5 million jobs in the oil, natural gas, and coal industry. And I want to go up there and paste a little thing over the top of that and said 14 million jobs in the renewable energy field. So, but I think there's tremendous opportunity, especially as we talk about first creating the infrastructure, like smart grid or storage devices, et cetera, and then also maintaining the infrastructure once we have it. So, and by the way, that doesn't use any water or a very small amount of water. So,
I would just add on to that when you do look over in Europe, in Germany and other countries, you see a decision to provide the robust resources, the robust storage. You see an investment in grid systems and pump storage, for example, that's going at an accelerated pace in Europe. So they've made the decision that they're going to build it and they will come. We've sort of doing it the other way around. Let's see if they'll come, and then we'll see what we have to build. So.
If we are to develop rating for the infrastructure, and we are, some of the components that you've discussed, whether it's water, energy, availability of natural resources, may provide indicators. Where would you see the threshold levels for these indicators? For example, what's going to be rated A based on what, and what would be rated D and based on what? In terms of all of these elements, from energy, water, natural resources, and so forth.
I didn't hear the first part of your question.
The part, if we are to develop rating for the infrastructure, what would be the threshold levels based on the components that you've discussed?
Ratings of infrastructure.
In terms of sustainability, if you want to call it, or as using certain indicators, which are the energy, the water, the air quality, the land use, and so forth.
Well, certainly there are, you're right in the sense that there are multiple domains there. Energy, the energy domain, the water, and our anthropogenic use and needs for those things, and then the ecology itself. We know fairly well how to develop integrated ecological ratings for the health of systems. It's not perfect, but we know how to measure, monitor, and rate those things. I think the more challenging piece is the sustainability of things like the power system and making the right investments in sustaining those systems going forward. The grid, how are we going to build out the grid, for example, to sustain the operations that we have, sustain the delivery of energy in growing renewables. In terms of, are you talking about sustainability indicators? Well, I think life cycle impact analysis is one way that we do that, looking at the total use of energy and resources and resource depletion for the different energy technologies. We have to look at, there are thresholds for some of the population modeling that I showed. Helps to establish thresholds for individual populations, but there's quite a bit of uncertainty and science to be done there, so that we can model populations to understand when we've got them to a sustainable level. If we're taking energy out of a system, for example, through hydropower, we're taking energy out of a system through wind even, we don't yet have enough modeling expertise or haven't really done quite enough yet to understand what it means to take energy out of those systems and what those impacts are.
Okay, I think now we're going to take a question from one of our webinar participants.
Yes, a couple of questions. Dr. Critton, what is the source of the slide with the hydro potential in the south? And
That was a report that Marilyn Brown was involved with. You can probably Google Marilyn.
By Hall.
Oh.
Could you repeat?
Yeah, the source is a report by the Idaho National Energy Laboratory, INEL, by an author named Hall, and there were some other authors, published in 2006, which was an inventory of existing water to energy resources in the U.S. So this was the, in fact, I was going to follow up with a question. Is that all of that question? Can I continue and redirect to Brennan on that same issue? When we've talked before about the opportunity for non-power dams to be converted to power generators, you've been very enthusiastic about the potential economics associated and viability of that. But in your presentation this afternoon, you seem to ratchet back a little bit. And I just wondered if you had been confronting some other sources of obstacles, resistance to this notion of converting some of our existing water reservoirs and impoundments to power production, given that the ecological footprint's already there. We're already evaporating a lot of water because we've got it impounded, so we don't add to that water depletion. What kind of response are you getting to that resource opportunity that we've talked about, that was in that graph that was in the report that John showed?
Yes, thank you. We are in the midst, or completing a revised resource assessment. Oak Ridge is doing that in conjunction with Doug Hall at Idaho National Lab. That resource assessment is going through quite a bit of more rigorous engineering analysis of the dams. We are, for example, going through those 82,000 dams, not one by one. We're using some automated procedures to kick out specific cases and then analyze those when we need to. And so you find that a lot of the data, for example, the dam height is not the total energy that's available, we're finding. The actual total energy available is the water level difference. So there are some issues that are knocking those numbers down a little bit in terms of the 140 gigawatts. And so, as I said, what we are finding is that 60% of the total energy available is in these large main stem navigation dams. It's not the very small ones. The remaining 40% is in the small ones. I can't tell you what that total number is yet. We're still going through some peer reviews on that, and so that will be out later this year from DOE. But there are opportunities. It's not 140 gigawatts. But you're absolutely right that the footprint is already there. The issues are, the ecological and environmental issues are minor typically. I don't want to say always. And the issues are more safety and administrative with the Corps of Engineers and the Federal Energy Regulatory Commission. They've been doing a great job lately of getting together to help streamline that process for permitting new powerhouses at those dams.
Another question from one of our webcast listeners is, what resources would Dr. Smith recommend for further information about the use of water by coal plants, particularly for ash disposal?
That would be is going to be specific, site specific to some. It really depends on the type of system, and the information we pull together really comes from going to individual plants and looking at their systems. I can't, in terms of a design reference, our sources are the design documents at the power plants we've looked at.
This person's emailing from Vermont, Burlington, Vermont. So would you suggest any resources in that region of the country?
Well, one place they can look is the environmental permits is a good place to start looking. The NPDES permits are the corresponding state agency that deals with both their water withdrawal and their discharge, their effluent discharges. And oftentimes, individual systems and discharge points will be broken out, and so they can go and get specific information on this outfall is from an ash pond, and it's this amount of flow typically.
I want to build on a comment that Ken made earlier, a question about pricing on fresh water. As Dr. Smith correctly pointed out, in Europe, for instance, they make their decisions on energy investments differently than we do here. And you also showed a chart with various power producers and their near-term capacity expansions and how their mix is. And Southern Company didn't show any renewable energy in their mix. I'm sure there's some, it's just too small to see on your chart. The National Renewable Energy Lab published a study, though, that says Georgia has a technical capacity just in our rooftops of producing over 23 megawatts of photovoltaic energy. So there's obviously a disconnect there, and if you ask somebody from Southern Company, there might be some in the audience, but their number one reason for not having more photovoltaics is cost. So if we value fresh water and we don't have a cost today, we should put something on there so that we get this input right based on our decision making.
Okay, my phone says 1:30, so I want to thank all of y'all for coming today, and thank you. Oh, sorry.
Yeah, no.
Did you have another?
I was just going to say maybe one more question, if anyone.
Sure.
has one more
Hey,
question.
sure.
Yeah.
Who's gonna get it? Who's the lucky person?
There's a lot of power loss. I'd rather yell, but that's okay. I'll talk quietly. There's a lot of power loss from the generation to the end user. Is anybody doing anything about alternative technologies for distribution other than just going to a smaller grid structure?
At the distribution scale, I think smart grid will help with that. As we get smarter and smarter, we'll begin to optimize which devices come on when, so that you, in essence, it becomes a traffic cop at the distribution scale. When you go larger to transmission scale, superconductivity is one of the main technologies. But when and how that could be pushed down the distribution level, I'd have to go back and ask my my electrical colleagues that question.
So three things before we leave. One is thank you so much to our moderator and our guest speakers. Let's give them a round of applause, please. Excellent presentation. Thank you. Second, I would also like to thank McKinsey & Company for its sponsorship and support of the series. And third, mark your calendars for Wednesday, February the 23rd for the next Clean Energy Speaker Series, where we will begin the discussion of the smart grid, what it means, how close to market it is, and those kind of relevant, salient topics. Thank you for being here. Bye.